Good morning, everyone. I'll introduce myself on a Who Am I slide, but thanks for attending the SANS Blockchain Security Summit. We're going to be talking about the uncensorable stack, malicious applications of blockchain technology. And what this means is looking at how adversaries are likely to be leveling up their tradecraft and using blockchain technology to carry out nefarious purposes. So very quick, who am I? I'm actually going to be starting at Halborn come September 12th as a CTI security architect, previously a senior security engineer at BlockFi, wearing many hats, but bringing out and setting the strategy for their cyber threat intelligence program. Previous to that, worked on the MITRE attack evaluations, creating different adversary emulation plans against different EDR vendors, and even worked with law enforcement building out some blockchain and cryptocurrency capabilities. And love doing fitness for funsies. I did a 70.3 Ironman, and probably the hardest thing I've ever done. So moving on to our high-level agenda, we're going to talk a little bit about what has happened and what is happening with specific CTI-derived examples as it relates to adversaries using blockchain technology. Then we're going to introduce some properties of blockchain technology and look at what actually makes it good to carry out some of these use cases that threat actors have. And then next, we're going to describe the components of a user-friendly and uncensorable application. There's some caveats with there that we'll get into, but there's going to be a blockchain specific for DNS. There's going to be a blockchain specific for compute. This is going to be your smart contract layer, whether that's Ethereum or Solana. And then we're going to have a storage layer, which is actually going to deliver some content directly to a user who would be able to browse to a site. So we're going to start off very simple. Some of these you all have likely seen before, and talking about what are some cryptocurrency native TTPs that we see today. So starting off, we're going to talk about cryptojacking. This is when a threat actor compromises a machine and begins to use that machine's resources to mine cryptocurrency. This is typically Monero, but it can be any CPU-friendly proof of work currency in order to derive resources from that user's machine. Next is crypto clipping. This is where your clipboard isn't safe. Oftentimes there will be malware, and in this case, an example of the Fropix botnet, which has over 1 million confirmed compromises as reported by Checkpoint Research, that what that implant is looking to do, or at least a portion of that implant, is monitor your clipboard. They're monitoring the clipboard for different cryptocurrency addresses that might be populated, with the goal to substitute out whatever your initial destination address is with the threat actor's cryptocurrency address. So this way, a user would be sending funds to the threat actor as opposed to the target destination. This also goes for mnemonic seed phrases. So if you're copy pasting, let's just say a seed phrase out from one pass and pasting it into MetaMask, for example, in order to unlock or reinitialize your MetaMask wallet, this implant is going to snag that seed phrase, send it to a C2 server, and then begin sweeping funds from all of those derived keys. And next, taking it a step further, looking at Trojanized cryptocurrency applications. So this is actually where a couple nation states started getting involved. So we've got Blue Noroff, which is a North Korean threat actor, dropping backdoor versions of MetaMask. So the way that this works is they would initially compromise the system. They would do some discovery on that system. And if they determined that that system actually had MetaMask installed, what they would do is drop a custom backdoor version of MetaMask to disk, go into Chrome, and then via DevTools point the version of MetaMask, instead of going to the Google Play Store, to go to that locally dropped version of MetaMask. And what that would allow them to do is monitor transactions, see if there's any other large accounts that they might not know about or other systems that are being interacted with. And then also, it's in a similar fashion to crypto clipping, change addresses, and sweep any seed phrase that are uploaded. Next, we have a report out of CISA talking from another North Korean state-sponsored group, which are actually backdooring versions of cryptocurrency trading applications. So they're making clones of like desktop versions of, let's just say, like a Webull. In this specific example, they're making mock trading applications. So these don't actually exist, but they're cross-compiled for Electron.js, or they're cross-compiled via Electron.js to run on Windows, to run on Mac OS, with the goal of connecting someone's wallet in order to steal those funds. Now, moving away from, okay, we're stealing cryptocurrency, to actually using blockchain technology to perform different acts. So in this example, we've got a Bitcoin address that's actually being used to encode C2 information with it, specifically an IP address. And that's due to the balance that's at that account. So for this specific implant, which was reported by Jared Stroud at ArchCloud Labs on a blog post, the implant would use a blockchain explorer at a specific address. It would get that balance, convert the balance to hex that you see here, substring out a portion of that hex, convert it to int, and then concatenate a period. And it does that for each portion of the octet of an IP address in order to get that backup domain in order to connect to. So if all other resiliency and normal backup mechanisms fail, this specific implant would be able to rely on the blockchain, specifically Bitcoin blockchain, to bootstrap backup in a censorship-resistant way. Next, this is actually introducing, or was a research paper that was theorizing how exactly some of these next generation botnets might work, called ZombieCoin. And this was done with Bitcoin script. So at a very high level, Bitcoin script, there's a scripting language within Bitcoin, and it has some basic logic and math packaged into those Bitcoin transactions. It's not Turing complete, and this is by design. So you look at the smart contract languages, the purpose of those is to be very extensible, to allow you to have the flexibility to write your very complex financial logic and contract information. But in order to decrease the attack surface, the Satoshi chose to limit the number of opcodes that are available within the Bitcoin script language. One of the opcodes that was theorized to be used by botnets from the ZombieCoin paper was the op return code. And this is able to actually store 80 bytes of data within a transaction. And we'll see in the next slide here that that's exactly what some other threat actors did. So for the Glebta botnet, you'll see that this was initially reported by Sophos and then later by Google. And this was a Bitcoin transaction that was used by this threat actor, which inside that op return data can be decrypted or by AES 256 with GCM to provide a backup domain or a backup command to execute. So you'll see in the screenshot below that the first 12 bytes of that op return function contain the initialization vector for that AES encryption. The last 16 bytes are the GCM tag, and that middle green section is actually the AES encrypted domain to be able to back up to. So the implant would have a hard-coded AES key that could then read and request through any number of these public nodes to get the transaction information at a specific address and be able to pull out the encrypted backup domains. And now moving a little bit away from Bitcoin, we have some examples, or at least one example, of other blockchains being used by threat actors. So in this case, we have the Shifu banking Trojan, and this leverages Namecoin, which is a decentralized domain blockchain that essentially is being used as that same backup mechanism. So instead of choosing to use Bitcoin, the Shifu banking Trojan actually used Namecoin domain addresses under the TLD of .bit to be able to query any number of Namecoin blockchain nodes to resolve those domain queries. So you see on the right, you have a Namecoin node, which has two services that are running on it. You have Namecoin D, and this acts as a central record of authority. This is going to be that blockchain daemon. It's going to be responsible for consensus and managing the ledger of transactions. And when you go, I'll talk a little bit about this later, but when you go actually purchase a Namecoin domain, what you're actually doing is using some of the scripting language within Namecoin to purchase that on the blockchain and to be able to, because you are the owner of that private key, you can set A records, you can set text records, you can set C name records, and that blockchain is essentially that source of truth. Then you have the Namecoin resolver, which checks the blockchain and responds to DNS queries that come into it and uses that blockchain as a source of truth. This is what the Shifu banking Trojan did. So now that we've kind of talked about some CTI examples of different types of blockchains and how threat actors are using them, we can start to theorize what might be coming in the future, what's next, what does an uncensorable application look like? And we do this by looking at some of the blockchain properties that exist today. So what are blockchains good at? Well, they're incredibly resilient. They're a peer-to-peer network with multiple nodes behind it. They have a consensus mechanism that's very difficult to change the history. I say irreversible, and I put a little asterisk on that because we're not going to to be, at least for now, talking about 51% attacks, hard forks, and the ability to, let's just say, like buy hash rate on some of these smaller cryptocurrencies via like NiceHash. They're verifiable, meaning users can self-host all of the infrastructure necessary in order to interact with them. If I wanted to ensure that, for example, the Bitcoin blockchain is what I don't have to rely on a third party to do that. I can run that infrastructure myself and verify all the previous transactions up into the Genesis block. And to some extent, this makes it uncensorable. I can run my own node and propagate it. Sure, there might be some Bitcoin pools that are trying to comply with OFAC that maybe will choose to receive payment to censor some transactions. But there's some game theory aspect to that. But I'm sure I could find at least one Bitcoin pool that would be willing to mine my transaction into a block. So from that sense, it's pretty uncensorable. And what are blockchains bad at? Well, they're incredibly slow. So Bitcoin has 10-minute block times. These are getting quicker as we move to smart contract platforms, with Ethereum at like 8 to 15 seconds, and then Solana even quicker, and then syncing. So if you want to sync the entire Bitcoin blockchain, this actually goes into the next point of moderate self-hosting resource requirements. You're going to look at like 500 gigs. If you're looking at a complete archive node for Ethereum, you're talking petabytes. This takes time to actually sync down to the network. I wouldn't recommend doing this on a spinning disk as well, because you'll take over a week to download the Bitcoin blockchain. SSD recommended. And you also have large limited transaction sizes. So there was the big Bitcoin Cash versus Bitcoin debate on how big should blockchain sizes be, and this is going to affect the throughput, the transactions per second. And then lastly, we've got a free to read data, but you're actually paying to write data to the blockchain. So I can go and query any number of Ethereum nodes right now and ask them questions about different balances or states of smart contracts. But if I actually want to update that state, if I want to create a transaction, there's usually a fee associated with that as a spam prevention mechanism. Okay. So for a tech stack for an uncensorable application, there's going to be 3 layers, as I talked about previously. We're going to have a DNS layer, a compute layer, and a storage layer. At the DNS layer, that's going to be providing a clean UI UX experience. So this is going to be human readable for visitors and implants alike. And we're going to talk a little bit about Namecoin, which I introduced briefly, and then Handshake, which is a kind of like, it's a different decentralized domain blockchain service, but quite better in a number of different ways, in my opinion. Next, for the compute layer, for this talk, due to limited time, we're only going to be talking about Ethereum. And this is the only required layer at this time. So there's this is where your financial logic and command and control services are actually going to come in play. And the reason that it's required is because the DNS layer and the storage layer are only there to make a more user-friendly experience. If I wanted to, I could interact directly with the smart contract using something like Remix or just creating my own transactions. But the other 2 layers are providing support so that, as we'll see, that might help increase some revenue generation. And then lastly, we've got the storage layer, which is probably the weakest of the 3 layers here, which we'll talk about later. And this is actually to deliver some HTML, CSS, and JavaScript to the client, right? So this is delivering that application, that static website, which will include some Web3 libraries to help facilitate the transaction creation in order to interact with that compute layer. So jumping in, we will talk about DNS first. So blockchain-based DNS. So I introduced Namecoin a little bit before. There was actually a fork of Bitcoin with a few additional opcodes created. These opcodes were added in order to facilitate the buying and selling of the subdomains under the .bit TLD. Depending on your interpretation of NFTs, this might actually be the first instance of NFTs on blockchains, where those domains were actually non-fungible tokens. This is a record for blockchain ownership, or excuse me, a blockchain for record ownership of those DNS records. If you have the private key to a specific subdomain under the .bit TLD, what you can do is update A records, TXT records, CNAME records. And the reason why it fell out of favor is due to domain sniping and squatting with no intention to use. So lots of speculation, people coming in, buying different domains, subdomains, and really no intention to use them, only really looking to flip them. And due to that, there wasn't a lot of developer demand to participate and to build on top of this network, because a lot of the domains that they wanted to use were essentially just being hoarded or priced out of some key projects. And then came along Handshake. So Handshake, in a similar fashion, is also another decentralized blockchain service. domain blockchain service, and they added what's called a victory auction, allowing buyers to bid for top level domains, not subdomains, top level domains, based on what they think that they were worth. And because of this, it actually allowed people to, or it required people to have more than a speculative view on what they wanted to do. There was actually there's a lockup period to where it allows people to actually come in and have a chance to bid on this domain based on the value that they think that they can get out of it. And they do this by also being equivalent with ICANN, using a decentralized root zone of trust and being interoperable with existing TLDs. Because there is more support behind Handshake, there's a larger number of public resolvers, which is good for our nefarious malicious application, because it allows the application to be able to go out and query the internet for any number of these public resolvers. And just like any other blockchain service, we can choose to run these Handshake nodes locally for additional censorship-resistant guarantees. So next, diving into Handshake, which is we're going to use for our censorship-resistant application. There's a site called Namebase. You can think of Namebase as you're essentially an exchange. This is where you can buy your Handshake token. You can participate in those auctions I was talking about via transactions. So those auctions happen directly on the blockchain itself. So if you didn't want to use an exchange, you could still participate in them by writing your own transactions. Namebase just makes it a lot easier. And I happen to own Clippy, that's why you see Clippy on the screen, as a TLD on the Handshake blockchain. And I have the ability to set those records that I was talking about before. And I even have the ability to set something called Skylinks, which I'll talk a little bit later about in the storage layer. So right now, if you dig at any number of the public Handshake resolvers, in this case, I've got one down here, and I ask for the Clippy TLD, what you'll see is the records that I have set, right? So I set an A record, I set a text record, and this is done at the TLD level, right? And remember, I can run a I can run a resolver myself. I don't have to rely on someone in the Handshake community running a resolver for me. So now that we've got a domain, we'll pop over to the compute layer. So as many of you are very familiar with Ethereum, I won't dive into it too depth, but essentially it is a smart contract platform. You have this code that is compiled and then deployed to the blockchain. And what you're able to do is call functions within that smart contract via transactions. And this follows the same principle as before, where it's free to read data from the blockchain. So if it is a public view or just a value that's set and I want to get that value, I can do so by querying any number of public Ethereum nodes or running my own node to get the value set at that location. And we can also store small amounts of data within the smart contract itself via setting those records. And Ethereum has a property of emitting events when functions are called. So this is you're very similar to pub sub. And what this allows us to do is actually hook into those events that are emitted, pull out some of those values and take action on it. This is incredibly valuable when it turns into running or for a botnet service to interact with, to be able to subscribe to a function to get a notification when it's called and what parameters it specifically was called with. And as of the time of writing the presentation, there's over 2,000 public get nodes in order to interact with. You can do, your botnet can do internet scanning. You can look up yourself on Shodan to see how many public Ethereum nodes are out there. And this is great for our censorship resistant and resiliency guarantees. So now we're going to talk about what exactly does the Ethereum command and control flow look like. So you've got your threat actor. The threat actor is going to deploy their smart contract, right? So this smart contract is going to contain some access controls such that the threat actor is the only one that is going to be able to set content or set a value within that smart contract, which bots will then later read. And this is signed by that threat actor's private key. Next, the threat actor is going to go out and compromise a bunch of hosts in order to get that botnet fleet up and running. Next, that botnet fleet is going to connect to any number of public Ethereum nodes. The threat actor could choose to toss one of their own into the mix in order to guarantee that at least someone is responding to them. But this is where that botnet is going to scan the internet and get some open Ethereum nodes. Once they find one that they're able to connect to, they're going to subscribe to that specific function within the smart contract and wait for events to be emitted, specifically from the threat actor. So let's say that threat actor wants to run some discovery commands, right? For now, let's not talk about exfiltrating data, but or add a new user to all of those compromised hosts, expose RDP, etc. What they'll do is they'll create a transaction containing a command or value and set that within the smart contract. And then once that is set, all of those compromised hosts can then actually get and take action based on the data that was set within that contract. So because of the contract is essentially the proxy for this command and control communication, there's virtually no way to censor it at the C2 level. So now that we've got the compute layer kind of talked about, we'll talk about the storage layer. So the early days of decentralized storage. So I know many of you are probably familiar with Uniswap, and unfortunately, the problem with a lot of these decentralized front ends is they're all running on AWS. They're all running on GCP. Pick your cloud provider of choice. It doesn't really provide additional resiliency guarantees. At any point in time, for any reason, AWS can go in and say, hey, this is causing too much pain on our side, whether we don't want to participate in this decentralized ecosystem, we're getting too many spam requests, we're just going to take this offline. And so the next step after using some of these centralized providers is looking to IPFS. So IPFS allows for content address storage. So you have a gateway, what they'll call is a node that you can upload content to, and essentially going to get a hash of that content. Should the content change, the hash will also change, and you can take that hash with you to any number of these gateways. So in this case, you see I've got Cloudflare is running their own IPFS gateway. IPFS runs their own gateway. I can take that same link and go to Cloudflare or go to one of IPFS's hosted gateways and get access to that content. The problem here is that there's no incentive layer for the gateway to actually pin that content, to keep it stored on their services, right? They're doing this more or less because they want to participate in the community. They're not financially incentivized to do so. Maybe they have some other outside reason why they want to see this content exist in the world. And if you don't want to run your own gateway, you have to convince at least one other person to host that data for you for free. And so this runs into some problems to making sure that the content that you're putting out into the world stays there long after you're gone. Okay, so this is where Saya comes into play. So Saya is another layer 1 blockchain for decentralized storage. You can think of it right now as a marketplace between renters and hosts. And the renters, are the buyers of storage. They sign contracts with the hosts. We'll talk about those contracts. And they upload and pay for data, right? So if I want to store some data on a host, I am paying that host to store that data for me, unlike IPFS. And then I can fetch and download that data upon request. Then you have a host. Hosts, there's a number of them. There's over 700 at the point of me writing the slide deck, and they're responsible for that renter's data. They put up collateral, which is lost if they fail a storage proof. So they're financially incentivized to keep this data and to keep the renter's data intact and healthy. And they're able to set their own prices. So they can set storage prices, bandwidth prices, and the contract that is being signed between the renter and host is what's actually being stored on the blockchain. So I will agree for this amount of storage at this price, and there's storage proofs that are involved to make sure that the hosts are being honest. The data itself is not actually written to the blockchain. It's written on the host, which have large amounts of storage and hard drives that they're providing to the renters. So as long as hosts are being paid to store the data will continue to be stored because they are financially incentivized to do so. And we'll talk about some additional redundancy schemes where even if the hosts are not financially incentivized to do so, you can repair your file to the point where you can call out some of the hosts that want to be a little bit more malicious. So, and I've got some stats down there for you on how exactly big is this today, the network capacity of almost 8 terabytes. So talking about some of those resiliency guarantees that we're going to want is to make sure that this content is actually staying alive and healthy, that people and users are going to be able to access this content. So looking at Saya, they use a concept called erasure coding. And so each file is broken up into at least 30 chunks. And sent over to these 30 hosts. So the hosts themselves are really only storing an encrypted shard of a file, not an entire file itself. And you can set a redundancy scheme on top of that to say, I only need 10 pieces out of 30 total pieces in order to recover this file. And what this allows you to do as a renter is I can make contracts with more than 30 hosts, 100 hosts, the whole network if I wanted to, in order to pay more to have a higher likelihood that that file is going to be there when I need it most. Okay. Moving on to a full rounding out the storage portion of the stack here. We're going to talk about something about Skynet. So this is a layer 2 that's actually built on top of the SIA blockchain. And the purpose of this is to really make it almost feature complete with IPFS. So it enables file sharing. And the main difference here is anyone can now pay a host to host that data. Unlike an IPFS, where you just have to convince someone and hope that they'll pay for it, and someone will keep it online via that gateway. Instead, here, you can actually pay someone to host that content. So you'll see a link below. This link here, if anyone is familiar with Firefox Send, which actually got sunsetted because it was hosting too much malware, here is a completely locally packaged version of very similar to Firefox Send called SkySend. So the red portion you see there is actually a handshake top-level domain. And very similar to those IPFS gateways that I was talking about previously, the blue section, siasky.net, is a portal, which you could think about as an IPFS gateway, just using the SIA Skynet service. And so what you can do is you can take that handshake TLD, which is representing some data on the back end, right? That HTML, CSS, JavaScript that someone is paying to host on the SIA network. You can take that to any number of these portals and they will serve that content to you. So this adds to that resiliency, right? Anyone can go in and essentially, if I like SkySend, I can choose to pay to keep that content hosted on the SIA blockchain. So now that we have an understanding of what exactly is all of these different layers of the stack, we've got a storage layer that is able to serve HTML, CSS, JavaScript to a client. We've got a handshake and decentralized domain layer that a user can browse to. We're going to put it all together. So one of the things I theorized is, what is a distributed denial of service as a service application look like, right? So you have some bots, you want to sell those denial of services to get higher margins, rather than just doing your typical crypto jacking, but you don't trust anyone. You don't want to have to rent out your blockchain. You don't have to communicate on raid forums, try and set something up. You don't want to have to deal with escrow. So what you're going to do instead is you're going to export and entrust the escrow of these services to the different layers of the blockchain stack. So you don't actually have to do or rely on any individual parties. So let's jump into what exactly this might look like. So you start off just as before. You've got a threat actor, which is going to deploy a smart contract, right? So this Ethereum smart contract is going to have a public function that anyone can call, where the caller will pay 1 Ethereum and supplies a domain to denial of service. That threat actor, just like before, is going to establish a botnet and compromise a number of hosts, which are then going to connect to any public Ethereum node and subscribe to that public function in that smart contract, such that when an event is emitted, they can act on it. Next, the threat actor is going to deploy a website on Skynet, right? Just like on IPFS Gateway. What they're going to do is they're going to create a user-friendly experience. And this experience is going to allow any buyer of this service to interact with those Web3 JavaScript libraries and create a transaction to interact with that smart contract function. Next, they're going to buy a handshake TLD, right? Because it would be nice if they could just very easily have a user-friendly and human-readable way to access this denial of service as a service. This way, you don't have to deal with hashes, you don't have to deal with long URLs. And what they're going to do is then combine all this together. They're going to create a record on the handshake blockchain that is going to point to that deployed website so that buyers of service will be able to purchase that denial of service functionality. And let's look at it from the buyer's perspective, right? So after being shared a specific link, whether through raid forums or DM'd or however they're going to be communicating out this denial of service, they are going to connect to that site, right? And that site is actually going to be that domain or human readable domain. Very easy to get to. They're going to create a transaction by interacting with that site. The JavaScript is going to do the heavy lifting for them. And they're going to create that transaction directly to the smart contract. They're going to provide the domain. They're going to provide the Ethereum. And then the compromised hosts are going to get that emitted event and then start to act upon it, right? Then they're going to begin the denial of service on that website. And then from there, the attack is complete, right? And I'll take a moment to mention at every layer in this stack, no one has to trust anyone else. The threat actor can deploy their own Ethereum node. They can deploy their own handshake node. They can deploy their own Sia node, right? They don't have to rely on any third-party service to be an intermediary here. Just as the buyer doesn't, if they are incentivized to do so, they can run their own Skynet node. They can run their own Ethereum node, and they can run their own handshake node, right? No third parties need to be involved in this process because these are all peer-to-peer systems, right? So they can run their own infrastructure themselves and not have to rely on anyone to propagate these transactions for them. So at the end of the day, you've got the seller of service, which ends up being a smart contract in a botnet. And then you've got your buyer of service, and which is essentially just someone browsing to a website. And we're going to jump into a demo of what this might look like here. All right, so on the right, this is the website, right? This is what is actually being deployed at that link. On the left is going to be the implant. And this is going to be mocking that compromised host, which is listening for that emitted event. On the page, all the user needs to do is install MetaMask, connect MetaMask to this website in order to create the transaction. In this case, I'm going to be typing in sans.org as the quote domain to denial of service. Once I provide some Ethereum to this transaction, sending it to the smart contract. Yep, you'll see I'm just doing this on the testnet here. I can then interact and purchase some of this denial of service as a service offering. So there's no real sophistication needed on the buyer's perspective, and this is all handled in a trustless way. You see very quickly the block was mined, and on the left, the implant is kicking off and starting to denial of service the sans.org website. We pop over to Etherscan to take a look at the exact transactions that were handled here. And you'll see in the emits log events that were emitted, we've got sans.org in there. So that's exactly how the implant was able to pick up the domain in order to denial of service. We can take a look at the contract itself and see and interact with it this way too, and see the total balance there and all the previous transactions there, and be able to take a look at who exactly has interacted with this smart contract before, and more importantly, what domains have been denial of service previously. So that was our censorship resistant, denial of service as a service application that I kind of theorized. But as you may have guessed, there's many of other ways that threat actors are likely going to be using blockchain technology to kind of earn more money at the end of the day. So in the Conti ransomware group leaks, you dig through some of that content on what they were talking about in their internal chat, and they were very much so exploring different ways to use blockchain technology to earn more money, right? Whether that's deploying their own blockchain as a way to be more resilient in compromising hosts, or automated ransomware payments. So Jeffrey Laddish published a number of blog posts on this topic, and I encourage you all to read them because they're really thought out, and saying, what does it look like when you're able to essentially provably be able to decrypt some of this information or receive that decryption key. And Rob, how much time do I have left here?
So we are up on time, but
yeah,
we do have a break. We have a 15-minute break. So if the rest of the Sans crew is okay with it, I say go on for another minute or two. But
that's totally fine. Yep, go ahead.
Yep.
Awesome. Yeah, I'll jump to the defense and monitoring section because I would like to at least get some takeaways on what can defenders do here. So defense and monitoring. So the network is only as strong as the number of nodes and the consensus of that specific blockchain. So of the blockchains I talked about previously, the storage layer and the Skynet layer are probably the weakest because there's not that many portals being run. It's not a very from the consensus layer is a little bit stronger, but if any individual authority wanted to go in and take down all the portals, that's going to be a pretty easy thing to do. Next would be de-anonymizing via existing blockchain tracing solutions, such as CipherTrace, Chain Analysis, and Elliptic. Blockchains are pseudo-anonymous, so once you're able to subpoena an exchange, hopefully there's an OPSEC failure on the threat actor, and you're able to get some personal identifiable information, you can then begin to work backwards on all of that on-chain activity. The goal here is to get to the operator, try and get their private keys in their house, wherever they got them stored, and get to them as an individual and not try too much to take down the application itself. And then lastly, endpoint monitoring. So implants and malware will have signatures for scanning Ethereum nodes and handshake nodes. This is pretty common, and I would expect many EDR products to be able to handle this and pick up on this type of activity. And then public nodes can be enumerated and blocked from networks as soon as they appear. So in a similar way that these infected hosts are scanning the internet for different open Ethereum services, what you can do on your network is say, run your own scans to see what blockchain nodes are popping up and which should be blocked, and what traffic should or shouldn't be allowed on your network. And then lastly, if you see a host that is beaconing out to a non-ICANN supported TLD, that traffic should probably be blocked as well. There's no real legitimate use case for those DNS requests being made. So DNS logging would help a lot here as well. And I would do some Q&A, but as I said, running out of time. Thank you much, everyone, for the opportunity, and I'll be around in Slack to answer questions as well in Zoom. Thank you.